Democracy at work.
Welcome to this episode of Eureka, and in this episode, we are going to take you to Palampur, Himachal Pradesh. We are going to have a very wonderful conversation with its director, Dr. Sanjay Kumar, Institute of Himalayan Bioresources Technology, a CSIR institute situated in Palampur and doing a lot of wonderful technology development that can uplift the Himalayan region. Thank you for being with us in the show. In your busy schedule, you have found some time for us. Thank you for that. Let me start with some of your major early works, which has given you international fame and also made a mark in the world of science. One is related to the novel carbon fixation process that, pathway that you found. Can you explain to us, first of all, what is this carbon fixation? And then, of course, then we might be able to understand what is the novel pathway that you found. We are eager to hear, sir.
Thank you so much. And indeed, it's a great pleasure to be part of this program. Thank you so much for that. Now, if I tell you our story, how did we discover this carbon fixation pathway? It was very interesting. Around 1994,
okay.
Yeah, once what happened is we thought we should work on high altitude of Himalayas. And so we visited to high altitude location. And what happened, my first observation, there we used to walk very fast. And once I went there, it was very difficult to walk there.
Okay, sir. Okay.
And because of low partial pressure of gases. And that was a triggering point. We thought when we face so much problem in terms of walking and breathing, how plants survive, how plant uptake carbon dioxide, and how they do all these processes. That was our simple
very
thought.
Interesting question, sir. That's a very interesting thought, really.
Yes. And so what we did then, initial first thing what we do, whenever you feel such observation, you try to measure the rate of photosynthesis. Rate of photosynthesis means how much carbon dioxide is fixed by the plant per unit time, per unit area.
Okay.
So once we measured, and this we measured, right from Palampur to one place known as Kibber. It is in Spiti region, around 4,200 meters height. So along the altitude, we measured the photosynthesis rate. And very interestingly, photosynthesis rate there was no significant difference. Similar plants which were growing down, similar plants which were growing up, we did not find any significant difference. And then we thought there could be some mechanism of carbon capture in the plant. Plants survive by taking the carbon. They take the carbon dioxide and fix it, make the glucose, and convert them into various type of food. So that's a fundamental process. And ultimately, we all derive food from plant through this basic fundamental process of photosynthesis. Now, once we realized that photosynthesis rate is the same, we thought, let us try to trace out the pathway, how plant does carbon fixation at low altitude versus high altitude.
Okay.
Right? So we grew the plant, same plant we grew at low altitude, same plant we grew at high altitude like barley, wheat, these plants, right? And then we fed them with radio-labeled carbon dioxide so that we can trace the path of carbon. So
no,
we
fed them. Just get a small idea, sir. This is like, say, for example, sometimes you have some problem in your stomach. The doctors give you a kind of a radioactive barium that they ask you to swallow. So it goes into your stomach, and then they take a scan, then you'll know where it has gone. It is very similar, right? Yeah?
Exactly.
That's what you are talking about, radioactive carbon, yeah?
Right.
Sorry for interruption. Please carry on.
No, that's fine. And then what we do is then we follow the path, like that carbon goes into which molecule. Okay. So here it is, in barium example, you trace the locations where it is moving. And here we trace that from one molecule to another molecule, how carbon is moving.
Okay.
And once we trace that pathway, Then we found something unusual there. And then we did many enzyme analysis. And when we put this data together, what we realized that plants at high altitude have a mechanism to simultaneously fix the carbon dioxide through two different enzymes.
I see. Okay.
All right. Normally, there are 2-3 ways of carbon dioxide fixation. One we call as C3 pathway, because the first primary product which we get in these plants has got 3 carbon.
Okay.
And one pathway is known as C4 pathway, because the first primary product which we get, which is the stable one, has got the 4 carbons.
Okay.
So probably there are C3, C4 type of carbon fixation pathway. And in one case, one set of enzymes are needed. In another case, another set of enzymes are needed. But what happens in high altitude, both the enzymes which are needed for C3 carbon fixation pathway as well as C4 carbon fixation pathway, both of them operate almost simultaneously.
Okay.
Right? And then what they do, the carbon which is fixed, path of it goes towards amino acid biosynthesis. And that's very interesting. First of all, carbon is being fixed and part of it goes for amino acid biosynthesis. And plant evolved very nice mechanism. What we realize that at high altitude there is photorespiration rate.
Okay.
Photorespiration is a process where in the presence of light, plant takes out the fixed carbon dioxide, and also along with that process, nitrogen is emitted in the form of ammonia.
Okay.
Right? Very interesting process. And what this plant do at high altitude, ammonia which is getting fixed, evolved during photorespiratory process, it fixes back and channelizes for amino acid biosynthesis. So it's a very nice way that while photorespiration is very important for plant to survive, plant does not allow the nitrogen to go back to the atmosphere, rather it refixes back. Right? So it was a very novel mechanism of carbon dioxide fixation, whereby nitrogen is also fixed in the process. A very novel pathway. And throughout, so once we discovered this pathway, we published this pathway, it got good publication. And then we thought that we should try to transplant this pathway into another system. Why? Now you might ask me why. Throughout the globe, there is a challenge which is going on. Everybody wants to convert C3 plant or C3 pathway into C4 pathway for one single reason, that C4 pathway are very specific pathway wherein photorespiratory loss, which I talked just now, photorespiratory loss in terms of carbon dioxide and nitrogen is minimal.
Okay.
Right? And people want to enhance the productivity. So they said that to have higher yields, there should be reduced photorespiration. But if you reduce photorespiration, then there are other evils associated, because photorespiration is also important for the plant. It takes care of higher radiation and so many other things. But this novel pathway that we had discovered, in this pathway, you don't stop photorespiration. Photorespiration continues, but the carbon and nitrogen, which is evolved during photorespiratory process, it gets refixed.
Okay.
So it's a very novel pathway.
Small question that I want so that we can get clarified. So when you talked about this plants which are growing at high altitude, which are two simultaneous pathways, is it the same plant which also grows at low altitude, or is it a different species which grows at high altitude, which have through evolution got that particular specific characteristic?
Yes. So for this experiment, very interesting question you asked, because this was very pertinent. What we had done, we had used the same species. It was just an environmental modulation. And that environmental modulation, in our opinion, was because, partial pressure is about 30% less. So in very crude word, not in exact word, but in crude word, you can say that in those locations, the availability of carbon dioxide is 30% times lesser compared to those plants at Palampur or at lower altitude, right? So therefore, in high altitude, what happens in case of human beings, because there is low partial pressure of oxygen. So we develop more of hemoglobin.
Yeah.
Right. Therefore, our cheeks become red if you stay at high altitude.
Yeah.
Right. And your hemoglobin level goes up just to compensate for low partial pressure of oxygen. So what plants have done to take care of the low partial pressure of carbon dioxide, they have evolved this mechanism. Okay. So it's a metabolic plasticity. All those enzymes are already there in the plant. Only thing, they changed little bit their system so that they can do this pathway. Okay. So once we published this pathway, then this pathway got a lot of attention. There is a group of F1000 prime group, and that group is a group of scientists who identify the best work being done across the world. Okay. And then they say that this work is important or this work is not important. So they had identified our work, and they said that this is the work of significance for nitrogen use efficiency and so many other things. So they had given due credit to our work. So we were very happy that international community has also recognized our work. And now
this brings me to a question that we have two important challenges in contemporary time. One is the climate change, which will have a serious impact on the way plant grow and so on and so forth.
Yes.
Second is that because of the excessive use of reactive nitrogen, there is also concern about environment.
Yes.
So I can see that your innovation, your discovery, has a lot of potential to address these challenges. Can you illuminate us?
Yes, I think again very relevant thing, because what we are trying to do now, and we almost succeeded also. Now we transplant. Earlier we did this work in a model plant.
Okay.
And now we have transplanted this pathway to brassica.
Okay.
Right? Because if we succeed here, and our lab results are showing very good success.
Okay.
And advantage now here is that suppose plant needs 100 kg nitrogen per hectare, then once we have plants with this new pathway, these plants will have approximately only 70 kg nitrogen per hectare.
I see.
So we feel there will be less nitrogen application to the plant to achieve the same yield levels.
Okay.
Right? So advantage there would be that environment will be much safe because you are applying less of nitrogen. And then farmers' pocket will be happy. So farmers will have to spend lesser expenditure in terms of fertilizer application. That is a second advantage.
Yeah.
Right? And the yield level remains the same. Okay. So that's the implication of our work. And we are moving ahead pretty okay in this direction.
Right, fine, sir. That's a very, very wonderful work that you and your group had engaged, and then one can see that how it is interconnected. Something that started with curiosity. At that point of time, it was just curiosity, but as it grows, one can see that how curiosity leads to certain social use. We need to take a very short break here, and we'll continue this conversation after this break. We'll take a very short break here. Keep watching Eureka. After the break, this conversation will continue.
Article 86 deals with the right of President to address and send messages to the Houses. The President may address either House of the Parliament or both Houses assembled together, and for that purpose require the attendance of the members. The President may send messages to either House of the Parliament, whether with respect to a bill then pending in Parliament or otherwise, and a House to which any message is so sent shall with all convenient dispatch consider any matter required by the message to be taken into consideration.
Welcome back to Eureka. We are having a very wonderful, very enlightening conversation with Dr. Sanjay Kumar. He is the director of Institute of Himalayan Bioresources Technology, a CSIR institute at Palampur, Himachal Pradesh. One of the things that your institute has been in the news recently is with regard to Heeng. After all, if you look at old recipe books available in India, Heeng is mentioned for many hundreds of years. So why Heeng has become a news, and where are you in that news?
Okay, sure. See, again, very interesting thing, because what has happened is, as I told you, that since 1994, we had been going to the high altitude locations. And now, once I took over as a director, then I had a very close interaction with all the farmers of the place.
Okay.
So I had a discussion with farmers at lower altitude and higher altitude also. In high altitude, I realized that people grow peas and potatoes, and that was their way to earn their livelihood.
Yeah.
And when I realized the location is almost similar to what we find in Afghanistan and other places.
Okay.
So we raised the question, those places, what are the crops that those people deal with? What are the crops that our guys are dealing with? Can we improve their livelihood? That was our simple question. And then what had happened, we also make it, library of the plants which are available in our areas. And once we were analyzing those, it happened almost simultaneously that we realized that we have some variety of Heeng, but asafoetida was not there listed in any of the resources.
Oh.
And we were also making digital library, and they said that in India, classical text says that they get the Heeng, what is grown in Afghanistan and Iran, that area.
Okay.
So it somewhere it was there in our mind. Our data showed there was no asafoetida in India. And then we realized that this topography is very similar to Afghanistan. And we studied what happens in Afghanistan, and we realized that they grow a lot of Heeng, asafoetida.
Yeah.
And then we checked the export data, and we wondered, India imported around 1,540 tons of Heeng worth 940 crores last year.
Okay.
And that was a huge sum. And India does not grow even a single gram of Heeng in this country. We had no asafoetida in this country. Then we decided, yes, if you have to make Atmanirbhar Bharat, without Heeng, we can't even have our food. North Indians can't have their dal, South Indians can't have their sambar. I said, man, it doesn't work. We had to get our Heeng into this country. So then we started Heeng search. We wrote more than 8,000 letters to different parts of the world, that who can supply us these seeds, authentic seeds of the Heeng. Through NBPGR, certainly we involved ICAR, National Bureau of Plant Genetic Resources. Through them, we did all correspondences, because of whatever seeds we get, they should be authentic, number one. Yeah. And secondly, they should be free from all insect pests. They should be properly quarantined, so that we don't introduce any unwanted things in India.
Yeah.
So it took us some time, but then in 2018, we got the seeds of the Heeng. We did proper quarantine. Then we discussed with the state government. We signed MOU with the state government. The state government came forward. I think we should acknowledge them very appropriately. They came forward. We signed MOU with them so that Heeng seeds do not remain in our lab.
Okay.
We developed agro-technology. We developed proper authentication technology, and then we signed MOU, and seeds were given to the farmers. And now farmers have started growing those Heeng seeds.
Okay.
Right? Yes. So that's how this Heeng came.
As you rightly pointed out, whether it is North India or South India, in fact, almost pan-India, maybe there are a few cultures which are not very comfortable with the Heeng, but it's one of the most used condiment. But many of us are not even aware. What is it? I mean, is it a fruit? Is it a seed? Is it a resin that comes out of a shrub? What is it? How is it produced?
Okay. So this is the sort of resin which is present in the roots of this plant. This plant very much looks like the shrub of carrot. Very, very similar to that. But after 4 to 5 years, it suddenly grows up. And then at that time, we harvest the roots. And from the roots, the resin oozes out in the form of Heeng, and that we will be using. Yes.
That's very nice, sir. I mean, I suppose for most audience, this will be a very great news. I mean, they would have not known this. I mean, it's a very important thing to say here. Coming to the contemporary times, I mean, you're also keeping up with the times. It's not only about the past, but also about future. Your institute is one of the important aspect of Floriculture Mission, which has been launched by CSIR.
Yes.
So, what is the objective of this mission? What are we aiming with this?
Okay. Very rightly pointed out, floriculture is again a very important crop which can give very high remuneration to the farmers. Honorable Prime Minister is requesting all of us that can we enhance the farmers' income? And floriculture crop can give at least 4 to 5 times more income as compared to the traditional crops. That's one advantage.
Okay.
Secondly, some of the crops, moment your flowers are there, farmers get a money out of it.
Okay.
Right? So our mission is then we develop the right varieties for the farmers so that they get the quality flowers and the quality produce. That is one of our major mission, a major objective.
One question that comes as an ordinary person here is, after all, plants give out flowers. I mean, so where is the technology coming in? Where is there is a need to mission?
Yes. You see, if it is just a question of any flower, then we agree. But there is quality of flower, for example, shelf life condition, various type of shapes, sizes, so that we breed through science and technology, number one, right? Then we develop proper technologies. For example, we have developed hydroponic and aeroponic technologies.
Okay.
If a flower takes 180 days in the field, in hydroponic and aeroponic, we can get flower just in 60 days, number one. You can get throughout the year, number two. Whenever you want flowers, now it is available. So we are developing now rooftop models so that, in urban areas, people can have on their houses, at the rooftop of their houses. So that's where the entrepreneurship comes. Then we are integrating floriculture with the apiculture so that honey production can be promoted. So we are developing proper parks for that. And that's where, again, the entrepreneurship comes into play. Then we'll be doing into the school and colleges so that, people are aware from the childhood times that, floriculture could be a way to move forward. And then, we develop end-to-end technologies like if you harvest the flower, do you have the right place to store those flowers? Number one, do you have the right mechanism to transport those flowers to the mandis? So then in the mandis, do we have the right market structure for the sale of those flowers? So we are doing end-to-end approaches in floriculture.
Okay. So this is a broad canvas of this floricultural mission. So what are its, let's say, short-term objective? I mean, where all you plan to reach? Why your institute is an important component? How do you see Himalaya benefiting out of it?
Yes, sure. There are two things. We take advantage of our geography.
Okay.
When in Delhi you have no flowers, we get flowers in Himachal Pradesh. We get flowers in Uttarakhand. So first important thing is that we supplement the plains from hills, number one. Secondly, even today we import several billions worth of flowers in this country. We are net importers of flower culture crop. We want to stop that import. For example, I give you an example. When you grow lilium, we cannot have bulbs. We don't even have bulbs of lilium in our country. We have to depend on import. Kela lily, 100% import in this country. So can we develop our own varieties?
Okay.
Right? Then our indigenous flowers, they find no market. And we have some beautiful flowers. We say that this valley of flowers, but where are they in the market? They are just in the valley. So we want to bring them from valley to the people's house so that rather than being net importer, we become the next, initially Atmanirbhar, and then we become the next exporter. That's our whole idea.
Very, very, very nice. Very, very nice, very interesting point that you made there. And how even in a very small thing, like for example, growing flower for recreational or other purposes, science and technology can play a very important role. I mean, that also comes from your point. Another area where your institution has been focusing is looking at a non-traditional area for example, growing saffron, which
That's
is a
right.
very high-value plant. So,
That's right.
what is that plan that you had executed from your institution?
Sure. You remember, since our childhood days, we had been listening that Kashmir is the only place where the saffron could be grown.
Yeah.
Say Kishtwar region, Pampore region, that is the area where grows in about 3,000 hectare areas in our country, and we produce around 9 to 10 tons of saffron. That's all. And can you believe around 100 tons of kesar is imported or saffron is imported in this country? So
Okay.
it's huge. So then we realized that how we can do it. So what we did some ecological niche modeling, that which are the other areas where saffron could be grown, number one. And using that, now second limitation was that we did not have the combs or the bulbs for the growth of this saffron. That was second challenge. So we developed a technology for growing this combs or the bulb of this saffron in large quantity. So
Okay.
we developed these two technologies. Then we did the on-site experimentation, that do we get the quality saffron by some of these areas. So we laid down experiment in Uttarakhand, Himachal Pradesh, even in South India, in places like Ooty, several places we laid down experiment based on that. And we realized that in some of the locations, quality saffron can be produced.
Okay.
Yes. And now once we knew that area, then we again signed MOU with our state government. Fortunately, state government came forward. Then we transfer all these things from the lab to the land. So now all saffron is growing in farmers' field. So in several areas in Himachal Pradesh and also part in Uttarakhand. So we took saffron from out of Kashmir and trying to grow it throughout the nation. We developed all those technologies, and then chemical profiling confirmed the quality. So this is going to be a big story. That's what we feel.
Yeah. I mean, once we have enough people growing and enough harvest coming in, that would be a new beginning, a new change in the scenario. And as I can also see from what you are saying, that although your institution is named as Himalayan Bioresources, in fact, many of the hill areas, maybe not even part of Himalayas, some of your technologies and application can extend. And hill areas are places where one would need appropriate development, which will not affect the environment, at the same time give improvement in people's life. I can see that your institution has a great role. And from all of us, thank you for being with us in the show. For want of time, we may have to end this conversation here. But it was a very, very interesting and enlightening to talk to you. Thank you for being in the show. Keep watching Eureka. We'll come back with another conversation next week, same time.
Thank you.
Thank you, sir.
Defeat coronavirus.